Hello everyone, my name is Pawan and I will be talking about generalized structured low-rank tensor learning. And this is a joint work with Tanmay Sinha and Jaidev Naram at IIIT Hyderabad. So recent years have seen an increase in the quantity of multidimensional data, be it color images, video sequences, hyperspectral images. In general, if we flatten this multidimensional data to matrices, then we will lose the inherent associations between these features of the of multidimensional data, and our goal would be to keep the tensor structure intact. Okay? Recently, tensor-based completion methods have been proposed, and they are still popular for many of the image processing tasks. So tensor completion problem is when we are given some partial observation of the data, or in this case the tensor, and we would like to complete the or predict the unobserved data in the tensor. Okay, so formally we define tensor with these notations, and here omega means that these are the this is the index set of observations. Okay, and so only those indices will be given to us. And our goal will be to predict the data or complete the tensor for the unobserved data. A standard assumption in this model is the low rankness structure. So we will discuss this in more detail later on. So our approach to solve this problem will be via low rank regularizer and so on, which is shown here. So we have these partially observed data, and then we are looking for W, from which we will retrieve the complete tensor, and we have to usually in practice we have to give some low rankness assumptions on W. So this could be seen as a regularizer as well. Okay, so there were several low rank regularizers proposed in the literature, and let us look into two prominent ones. The one is overlap trace norm. So in this case, the trace norm is defined to be sum of WK, where K goes from 1 to K. And here, this star norm here, it indicates it's a nuclear norm. So for matrices, nuclear norm is defined to be sum of the K singular values. And we also have latent trace norms. In latent trace norm, the tensor W is seen as an additive decomposition of the K tensors. And then we again unfold this. So here also we have unfolded K, okay, and then it becomes a matrix, and then we take the nuclear norm here, and we can also in this latent trace norm we first see W as a sum of K tensors, and then we do the unfolding, okay, and then we define a spectral norm on that. So these are kind of extensions of the nuclear norm for matrices to tensors, okay, in both the cases, okay. It has been shown in the paper by Suzuki that latent trace norm performs better compared to overlap trace norm in some cases by some error bounds. So we can have let's say some other let's say nuclear norms. Let's say in this case of order 3, then we can consider this, okay, where B and D could be some transform. Okay, so here again we can also consider L2 variant of the latent trace norm. So we see here there is no square here, okay, but we can consider the one with a square here, and that has implications in the algorithm design as well. So we can consider one with L2 variant of the trace norm. Okay, so just put a square here, and this was first proposed by people by Misra and so on in 2018, and that's a L2 variant of this. And one of the goal was that L2 variant leads to some better exploitation of manifold structure and so on via some interesting lemma and so on. So this allows for non-sparse combination of tensors numerically, okay, and it's found to perform better than the latent trace norm, okay, which promotes sparsity, okay. So motivated by several low-rank regularizers, we propose a generic low-rank regularizer. So by generic, we mean that we put a QK here, okay. So if we see here, then it's just W here, but we can see W being transformed, okay, via some operator, okay. So then we put a QK here. So we have a QK here, okay, and then it can make the regularizer more generic via some linear map QK, okay. And then we still put the square here, okay, because we also want to exploit some lemma that will help us generalize this. So the proposed lemma also facilitates the introduction of new convex regularizer. That's the whole point of introducing this. So accounting for the additional structure in the data, let's say non-negativity, okay, or maybe Hankel transform for traffic speed detection and so on, or for image completion task and so on. So there have been many variant of completion problem, and sometimes constraints are also needed. For instance, if I'm working with image completion, maybe I can include a non-negativity constraint. A very generic tensor completion problem could be seen like this. Okay, so recover a tensor from a partially observed tensor, and then add the low rank convex regularizers. And in this case, we introduce a QK, and QK is a very generic operator that will allow us to play around with many different variants. And additionally, we will also put some constraints. Okay, it may be very difficult to put a very generic nonlinear constraint. So let us say we have some linear constraint, but A is some generic linear operator. And again, we are using latent trace norms where we see W as a sum of P tensors. Okay, so we will use a similar approach to this paper, and we will define a dual variant of this, and then exploit some low rank, then some manifold structure here there. So if we apply the dual form, then we are led to this. It's a min-max problem. So these are the dual variables we have, where f is defined to be like this. So there are some consist of some Lagrange multipliers and so on. And if we can solve this, so in this case we have these QK values and so on. So via this we can retrieve the primal solutions. Okay, so they are related via this. We do impose some restrictions on the theta i's in our dual form. So theta consists of theta 1 to theta p. Okay, so this is k equal 1 to p here. So this is a vector of these thetas, and we assume some low rankness, and we will see that this is also practically okay to consider low rank assumptions like this. So we take theta k is UK transpose. So if we do that, then we kind of introduce some interesting structure in this constraint theta here. Meaning now we look at theta as theta 1, which is UK transpose, and so on. Okay, all of them are like that. So this brings a interesting structural constraint, which could be seen as some interesting manifolds. In this case, U is a product of this spectrahedron, and it forms a manifold. So the spectrahedron manifold is defined to be like this. So we can see this as a product coming from this product space. Okay, and a spectrahedron manifold is a bit familiar, so we know how to kind of move around and minimize with on these manifolds. Okay, so GU here is this. Okay, so max is kind of observed in the GU. Originally, let's say we have min-max problem. Okay, so the max is also taken as part of a GU here. So GU is this. Okay, so once we have this optimization on a manifold structure, okay, we will need some optimization manifold tools. So basically we need to define what exactly was our manifold, which is this, and then the corresponding quiescent space, and obviously ambient space remains the Euclidean one, and then what are the notations for the tangent vectors? Okay, what are the metrics we are going to use, and more importantly, like what are the projections we are going to do, how we are going to do the retraction. Okay, and also since we will be using gradient based method, we need to compute the gradient of f. Okay, and so on. So these are the optimization in gradients. So this lemma tells us how to compute the gradient of G. So because this is what we would need, okay, to optimize for G, and we can have a second order information again by doing another derivative over G. So that will give us the second order terms. Okay, so these two ingredients can be used in some Riemannian gradient descent algorithms. So this is the one. So the algorithm for generalized structure low intensity completion problem, we use a Riemannian descent algorithm. So basically we will check for the gradient being less than some tolerance. If it's then we can stop, and then we solve for the dual variables, and then we compute the gradient of G, and then we provide these things and do a Riemannian update where the retraction operation happens. Okay, so we can keep doing this until our gradient is small enough. So this is the Riemannian causal gradient method, and finally once we have solved this, then we can reconstruct the primal variable W. So looking at the duality gap, since we haven't gone into the dual, we need to estimate what is the duality gap. So this is our duality gap, and duality gap is 0 under certain conditions. So if UK happens to be a low rank minimizer of 6, which is this problem. So if it happens to be a low rank minimizer, then in that case duality gap is going to be 0, or UK remains a full rank. Also in that case, in either of these cases, the duality gap is going to be 0. If it's not, then there will be some non-zero duality gap. okay, via this algorithm. So there is also a different interpretation of a duality gap. I'm going to skip this. Okay, so let us now look into applications. So we have proposed a generic framework that takes a generic operator like Q, okay, and then we also have like structural constraints, and based on different choices of Q and the constraints, we can have some special cases. So for instance, if we take a QK to be unfold of K, then we derive G to be this, and then we know how to compute the gradient of G and use the Riemannian CG to do the solve for this. Similarly, if we go to the non-negative tensor completion problem, this is something we studied in a previous WAGB paper, and so this is again a special case because I choose QK to be unfold of K, but then in this case, I have some additional constraint that W is greater than or equal to 0. Okay, so in this case, like the pixels are non-negative. Okay, so in this case, we derive G to be like this. Okay, so again, I can use Riemannian algorithm to solve this. So again, if we choose QK to be of this form, okay, where this D comes, D stands for discrete cosine transform, or it could be some Fourier transform, or it could be some form of Fremdlet transform. Okay, so these were some of the latest kind of ideas, okay, on different choices of Q, but then again it fits in our generic framework. We put this QK in our model, and then we derive G from there, and then our solver can solve this special case as well. And then we can also look into problems where people have used Hankel transform. Okay, so again here in this case the QK will be we do the unfold, but then we also additionally compose it with the Hankel transform. Obviously Hankel transform lifts the dimensions to a higher order, and then the computational complexity can increase in those cases. But again, our generic framework can model some of the Hankel transform based variants. Okay, so in this case again we can derive G to be like this. Okay. And here are some of the testing of our ideas. So the first thing we want to do is like checking the gradient norm, and is it like going to 0? And what about let's say the duality gap? So duality gap is one way to check whether our dual solutions are close to the primal. Okay, so in this case it's like close to 0. And then if we look into non-negative tensor completion problem, again it's like getting close to 0, and here also this is getting close to 0. And then this is a problem where there are no constraints. Okay, so here also we do some check on the duality gap. And then looking at some data. So this is the image data, and this is a color image, hyperspectral image, and this is a grayscale video data. And we compare with some of the state-of-the-art methods in tensor completion problem. So here the LRTC is a low-rank tensor completion problem, and then here they use ADDM-based solver. So here our goal is to also kind of show effectiveness of our solver for solving similar models via some other solvers. Okay, so we have these state-of-the-art things, and we compare with RMSE error, and we have the tensor, unobserved tensor, with only 10% of the data observed. Okay, and then we need to complete the remaining 90% of the data, and we compare it with the RMSE error. Okay, so after doing that, we find that on many cases we are doing the best. In some cases we do second best. Okay, and in some cases like LRTC, especially on Baboon and Splash, which is a color image, LRTC seems to be doing the best. Okay, so and if you look into the images, then as I said, in the color images like this Splash, it seems like LRTC seems to be the best, and this is also indicated well from the table. But if we go into these hyperspectral images, then it seems like our framework seems to be better than, let's say, LRTC or these other variants. Okay, so in hyperspectral, it seems to do quite well. So these are the references for various state-of-the-art tensor completion problems, and we have our framework kind of in the special cases it emulates some of these models. Okay, and these are further references.